While we've got everything set up, let's play a little bit with the settings and look at a couple other things that I think are interesting. I'm going to take the frequency way down back to the 50 hertz range. Let's adjust our view so that we see a normal waveform. So we're triggering on, let's go back to channel 1 please. Channel 1, select. Good. So we have about a 40 hertz sine wave. So the 40 hertz sine wave is the current through the outer solenoid and the voltage induced in the inner solenoid. They're basically the same except for the amplitude and the phase, the left to right shift. But what would happen if we change to a different shape? This function generator has 3 options. Besides sine wave, it also has a square wave and a triangle wave. So I'm going to switch to the triangle wave, so that'll change, turn off channel 2. That'll change the amount of current going through the outer solenoid to, instead of very sinusoidally, it'll ramp up and then ramp down, and then ramp up and then ramp down. So then we'll see how the voltage induced in the smaller solenoid is affected. Let's turn on channel 2. And we have here, if you can't see, a square wave. I can adjust the frequency. And let's also, try a square wave input. Motion sensors don't see me. Try a square wave input and look at the output. That's a little confusing. I have to, let's do one at a time. Here's the square wave input. And here is the induced EMF. Now I have to change the volts per division. It's going way off the screen, a lot higher. Turn this all the way down to 5 volts per division. So that's 5, 10, almost 15 volts, which is higher than we saw in the other experiment at only 40 hertz. So if you've taken calculus, the relationship between these graphs might look familiar. Okay, let's do one other interesting thing. I'm going to change the circuit around to look like this circuit diagram over here. So let me turn the output level all the way down. And I'm going to leave the oscilloscope like it is, but I'm going to move it over to channel 2. So it's still going to measure the current through the circuit because it's measuring the voltage across the resistor, and the voltage is proportional to the current, and it's a 1 ohm resistor. Now for channel 1, I will look at, instead of the voltage here, I want to look at the voltage across the entire for channel 1, I want to look at not the inner solenoid, but the output from the function generator. So now we don't care so much about the inner solenoid, but we're just going to look at the outer solenoid. So we don't care about this one. From the function generator, I'm going to go to channel 1 of the oscilloscope, but I also want to, so this is a BNC to BNC cable, same on both ends, but I also want to continue on to the outer solenoid. So I'm going to take that cable we were using earlier with the alligator clips on it and attach it to this T, which has 2 male BNCs and 1 female connection, so that we can use the same signal in multiple places. So put the T here on channel 1, and then feed it from the function generator. We'll turn the frequency down. And let's go back to the sine wave. And we'll display it here. Fiddling with things until the trigger was on channel 1. Weird trigger settings, okay. And then we'll look at and the oscilloscope, channel 2, is still looking across this resistor, so that should be showing the current there. Don't see the current. Oh, there it is. Okay, so we are at the divisions are 100 milliseconds, so 200 milliseconds for the full period. So 1 over 200 milliseconds would be 1 over 0.2 would be 5. So we have a 5 hertz sine wave, and you can see both these sine waves are in phase. So they both look like normal sine waves. Then I'll increase the frequency, and we can see the period decreasing, of course. So now we're around 30 hertz, and it still looks the same. If we zoom in on the horizontal axis, it looks okay. We see a slight shift while the channel 1, which is the voltage across the whole circuit, it's coming straight from the function generator into the oscilloscope. Channel 1 is still a pure sine wave. Channel 2 has been shifted a little bit, so the current is starting to lag behind the voltage. And we can see that we can increase the range to increase the frequency by a lot. The amplitude went way up. Now at 430 hertz, it's so delayed that it's basically a negative cosine wave. So it's 270 degrees behind the sine wave. The current is that far behind the voltage. So there's a little bit about inductors and inductive circuits, and a little bit about differentiating signals like sine waves, triangle waves, straight lines, and square waves, just for fun.